Let's see an example, a problem that we're going to formulate it as a linear programming model, optimization model, and then we're going to solve it. Galaxy Industries, a toy manufacturing company, manufactures two toy models. One is called the Space Ray, and the other is called the Zapper. The resources to make these two types of toys are, of course, limited for this company. They have 1,000 pounds of plastics. This is for weekly production, and they have 40 hours of production time per week. So these two resources, as you see, are limited, and we want to make the best out of this. There are other requirements and restrictions based on the market, such as the total production of the two toys cannot exceed 700 dozens. So in each week we cannot produce, and we should not produce, more than 700 dozen of the two types of toys, the total. The next requirement or restriction is that the number of dozens of space rays cannot exceed the number of dozens of zappers by more than 350. This is a requirement based on the market. So this is another restriction to consider. So now let's go to the technological input and ingredients, so-called, of this production. A space rays, 1 dozen of a space rays would require 2 pounds of plastic and 3 minutes of labor per dozen. So for 1 dozen of space rays to produce, you need to have 2 pounds of plastic. You need to use 2 pounds of plastic and 3 minutes of labor. For the zappers, 1 dozen of zappers would require 1 pound of plastic and also 4 minutes of processing time or labor time. So they have different ingredients, so-called, each type of product or toy. The current production plan calls for producing as much as possible of the more profitable product. A space ray actually would make 1 dozen of a space ray could make a profit of $8. So that's $8 per dozen. And the resources that is left out, we want to produce zappers, which gonna make $5 profit per dozen of zappers. And of course, we want to remain in the market guidelines and restrictions, given the given restrictions. The current production level for the company is as follows. They produce 450 dozens of space rays and 100 dozens of zappers. So how many profit do they make? How much profit do they make? Each space ray would make $8 profit, and they produce 450 of them. So that's 8 multiplied by 450. Each dozen of zappers would produce a profit of $5 per dozen. So that's multiplied by 100. 5 multiplied by 100. So 8 multiplied by 450 space rays plus $5 multiplied by 100 dozens of zappers. That's going to give us a total of $4,100 per week profit. So this is the current production plan that they have they use. We want to model this problem as a linear programming model, and then we want to find the best solution for this. That means that the production plan that is going to make the profit maximize the profit. So we're going to see whether we can actually find a production plan that can beat this $4,100 per week that they currently use. So let's go ahead and start modeling this problem into a linear programming model. What is the objective of the problem? What does the manager want to do? The management is seeking a production plan for the zapper and the space ray so that it would maximize the profit of the company for the company, given that it would actually stay within the resources constraints. Using linear programming as a tool to solve a optimization problem like what we had in this example. A linear programming model can provide insight and also an intelligent solution to the problem. So let's see how this works. So we're gonna go ahead and do a step-by-step build a linear programming model for this problem. First step is to identify and list the decision variables. What are the decision variables in the problem? The decision variable is how many of these two toys should they produce, right? So since we are going to use a mathematical model, we have to represent each decision variable, or how many of space rays and how many of the zappers to produce, with a mathematical symbol or a variable. So here I'm going to use x1 and x2 for this purpose. X1 here represents the weekly production level for space rays in dozens, and X2 represents the weekly production level for zappers in dozens. So what is the objective function? The next step is the objective function. The objective function is to maximize the weekly profit. That's what the manager wants to do. They want to maximize the profit by producing space rays and zappers such that the production requirements and resource limitations all are met. So let's see how does it work. Next is objective function. We need to write the objective function for this optimization linear programming problem. What is the objection? The objective. The objective is the goal is to maximize profit, right? So we're gonna write a maximization problem. Maximizing profit. But we need to write profit as a function, as an objective function in terms of x1 and x2, the number of production level for space rays and zappers. So what should it be? We know that each dozens of space rays would produce $8 profit. So this means that eight should be multiplied by x1. So this would give us whatever number of dozens of space rays we produce, we're going to make $8 off of it. So that would be 8 multiplied by x1. But how about the zappers? We know that for each dozen of zappers, we're going to make $5 profit. So that's going to be plus 5 multiplied by x2. So that's the objective function. This is f of x. Next step is to write the constraints and the function in the constraints. So let's write the constraints. For the constraints, I have actually put all the notation for the constraint that we had. The amount of plastic, limitation on the amount of plastic, limitation on the processing time per week, the total production limitation, the limitation on the mix amount, and the non-negativity constraint. All right, let us start with the plastic limitation. Given the problem statement, it says that the total amount of plastic available, a special plastic for production of these two toys, are limited to 1,000 pounds. So the total used plastic cannot exceed 1,000. How many plastic these two types of toy are going to use? We know that from the problem statement that each dozens of space rays would actually require 2 pounds of plastic. So this is 2 pounds. For the zapper X2, each dozens of zappers would require 1 pound. So based on these, we need to write the plastic limitation constraints. All right, so how do we do that? Well, the total amount of plastic used would be, each dozen would use 2, so that's 2 pounds multiplied by x1. So this gives us the amount of pounds of plastic used for the space rays, plus 1 pound per dozens of zappers, so that's 1x2. I'm not going to write the 1. So that's 2x1 plus x2. This is the total amount of pounds of plastic used to produce x1 and x2, or the space rays and zappers. This should not exceed 1,000. In mathematical terms, this means that this should be less than or equal to 1,000 pounds. So we have 1,000 pounds. Okay, so we wrote our first constraints. How about the time limit? We know for the fact, based on the problem statements, that they only have 40 hours per week. So they only can use the machines to produce these two types of toys 40 hours total. Okay. Based on the problem, each dozens of X1, the space rays, would require 3 minutes of production time. And for zappers, it's 4 minutes. Okay. So because we are dealing with minutes, we have to convert the hours to minutes. So first of all, our limitation on the timing would be 40 hours multiplied by 60, that's 2,400. So we have 2,400 minutes per week. The total amount of processing time spent on producing X1 and X2 should not exceed 2,400. So this should be less than 2,400. Okay. So how much minutes would require for X1? That would be 3 minutes. So that would be 3 minutes multiplied by the dozens of X1, the space rays. This is how much minutes is spent to produce X1 space rays, plus the time spent on producing the zappers X2. Each dozens of zappers will require 4 minutes. So that's 4 multiplied by x2. 4 multiplied by x2. All right, so we are done with the next constraint as well. So let's go ahead for the third constraint, the total production limitation. Based on the problem, the total production of space rays and zappers, X1 and X2, should not exceed 700. Okay, so this means that this should be less than 700, the amount of X1 and X2 produced. So how many X1 and X2 produced? X1 plus X2. So the total amount of x1 and x2 produced should be less than 700. Right. Next, we had the mixed amount limitation. It stated that the number of dozens of space rays produced should not exceed the number of zappers by more than 350. This is how we write this constraint. The amount of x1 or the space rays exceed by zappers, zappers exceed by x1, that would be x1 minus x2. So this is the amount of space rays more than more than the zappers. This should not exceed 350. And last, we have the non-negativity constraint. The non-negativity constraint says that the amount of space rays produced and the amount of zappers produced should not be negative. This is the non-negativity constraint. So it says x1 and x2 both should be non-negative. All right, so we have all the constraints here. Right, this is the typed version of our model. As you see here is a neat version of our model. We have our decision variable x1 and x2 in the amount of produced for the space rays and zappers. We have our objective function, and we have our set of constraints and the non-negativity constraints. So we are done with the model. This is the model. We have the model now. That is great and all, but what's the use of it? Well, now it's the next step. We want to solve this model. We want to use mathematics to solve this model, which basically is going to give us a solution for the problem that we modeled. Here we are going to learn how to solve this problem with a method called Graphical LP. Graphical LP is a simple visual method that can be used to solve optimization problem, linear programming optimization problem that only have two variables. Our problem has two variables, x1 and x2. So we're going to use the graphical LP method to solve it. The procedure is as follows. We set up the objective function and the constraint in mathematical format. This is already done. This is modeling. The second step is to plot the constraint. So we're going to plot using a two-dimensional space that we have here. We're going to plot x1 and x2 into x and y axis, vertical axis. And then we're going to, based on the constraint, we're going to identify the feasible solution space. That's going to be the solution space confined within those constraints. After that, we're going to plot the objective function. And we're going to move the objective function so that it's going to show us the optimal solution. And then we can determine the optimal solution based on that. I have enclosed two other examples for graphical LP and also how to model a simple optimization linear programming problem here that you can follow the link that is embedded in the slides, and then you can watch them on the internet. All right, so let's go ahead and solve this problem, our problem, using graphical LP. Here is how we solve this problem using the graphical method. The graphical LP, as I said, is only can be used for two variable problems. So here we have only, in this problem, we only have two variables, x1 and x2, as you see here. So I have written this the model on the right side of the screen so that you can actually see it. And then we're gonna plot the problem. So first, we're going to start with plotting the space. The space here is, as you see here, we have an XY axis here. The X axis I have dedicated to X1, and the y-axis I have dedicated to x2. But it doesn't have to be like that. You can do the reverse. Okay. All right. So this is x1 and x2. Also, I have partitions and segments these two axes so that it would be easier to plot the constraints. Right. So now let's go ahead and start plotting the constraints. First of all, what we need to do is the non-negativity constraint. So the non-negativity constraint said that x1 and x2 must be non-negative, greater than or equal to 0. So for x1, this is 0 for both of them actually, x1 and x2. The intersection here is 0, x1 0, x2 0. On the left side of this, here, x1 is negative. So we don't care about that, we don't consider that. On the other hand, beyond this point underneath this point, this is going to be x2 negative. So we don't care about that either. So we're only going to focus on this space that you see here. This confined square, white square space confined by these two axes. This is going to be our non-negative space. Right. So now let's go ahead and start plotting the first constraint. The first constraint, 2x1 plus 1x2, should be less than or equal to 1000. How should we plot this constraint? Well, the first step is to ignore the inequality symbol that we have here. So forget about less than or equal to, and we're going to replace this with equal to for plotting only. Okay, this is for plotting. Okay, so I'm going to write it up here. We have 2x1 plus x2 equal to 1000. What we want to do is we want to plot this line. How do you plot a line? If you remember from algebra, the only thing that you need to plot the line is 2 points from that line. If you have those 2 points, you can connect them together and then you'll have the line, right? So let's find 2 points in this line. Sometimes it's easier, generally it's easier to assign one of the variables equal to 0 and find the value for the other. So for example, I set the variable x1 equal to 0, so this is 0. That means that x2 is equal to thousands. So this is this point right here. Yeah. As you see here, it is 1000. I'm going to make it here. Okay. So this is x1 0 and x2 1000. The next point, we need another point. For the next point, this is what I'm going to do. This is 2x1 equal to 1000. Okay. So next I'm going to set x2 equal to 0. That means 2x1 is equal to 1000. 2x1 equal to 1000. That means that x1 is equal to 500, right? So x1 equal to 500 and x2 equal to 0. This is the point. So we have these points. Now we can actually plot the line. So let's go ahead and plot this line. So this is the line. Now we need to figure out what side of this constraint is the feasible space for us. Okay. Get rid of this. Okay. So let's go back to the constraint. I'm going to get rid of these steps that we did to draw the line. And I'm going to focus on this. 2x1 plus 1x2 less than or equal to 1000. So should it be on this side or should it be on this side? Well, a simple way to do this is find a point on for example, the right side, this side, and then check whether that point would would be feasible for the constraints. So I'm going to, for example, pick this point. This point, x1 is 800 and x2 is 0. So let's see if this point is feasible for this constraint. x1 800, 2 multiplied by 800 plus x2, and x2 is 0. So 0, x2. So that's 1600. 1600 is not less than 1000. It's greater than 1000. So this means that this right side, this is not the feasible space for this constraint. This side is. This side is. The left side. Okay. I'm going to highlight this space with this yellow color here. So the yellow space here is our feasible solution, feasible space so far, considering only one constraint here. Now let's move on to the next constraint. This is the next constraint. 3x1 plus 4x2 should be less than 2400. This is the processing time constraint. Okay, so I'm gonna write it up here. 3x1 plus 4x2, and I'm going to forget about inequality and instead think about the equality, so the line. Okay. We want to plot this line. Again, we have to find 2 points and then connect them together to get the line. So one is, I'm gonna set x1 to 0, so x1 0. Then 4x2 is equal to 2400. 4x2 equal to 2400. This means that x2 is 600. So one point is x1 0 and x2 600. x1 0 and x2 600. That's this point here. I'm going to show it by here. Okay, this here. This is the point. We need to find another point. This time I'm going to set x2 as 0. x2 0, then 3x1 is equal to 2400. This means x1 is equal to 800. Okay. So another point is x1 800, x2 0. 800 x1, x2 0. So this is going to be on the x1 axis right here. Okay. So now we have the 2 points here. I'm going to connect these 2 points to plot the line. So we have this constraint. Now we need to figure out which side of it, left side or right side, is the feasible space. So I'm gonna clear these steps that we use to draw the line. And we're gonna do the same thing. We wanna see whether this side or on the right side or the left side is the feasible space. Let's actually give it a point now. Let's give it this point. x1 here is 0 and x2 is 1000, right? That point. Okay, so let's see. x1, 0, so that's 3 multiplied by 0 plus 4 multiplied by x2, which is 1000. This should be less than 2400. So that's 4000. 4000 is not less than 2400. So this means that this side is infeasible. Okay, so this includes this part. This is also infeasible. We want to find the common area. Okay, so the common area. So I'm gonna actually clear the infeasible part here. The yellow area is our feasible space so far. Okay, so we are done with the second constraint. Now let's go to the third constraint. The third constraint, this is the total production of x1 and x2 should not exceed 700. So again, I'm gonna write the line here. That's x1 plus x2. This should be equal to 700. All right. So we need to do the same process. Find 2 points and then plot the line using connecting those 2 points. So one point here, I'm gonna set x1 equal to 0. So that means x2 is 700. So x2 700, x1 0, x2 700. That's here. And the other one is I'm gonna set x2 equal to 0. That means x1 equal to 700, which is here. So I have the 2 points. Now I can connect them and make the line. All right. Now it's time to figure out the feasible side. Is it this side or is it on the left for this constraint? I draw the with the yellow color here. Okay. So let's see. Let's actually test this point. 800 x1, x2 0. So 800 plus 0 should be less than 700, which is not. Okay, so this means that this area on the right is infeasible. So this actually didn't change anything. Our feasible space is still the yellow area that we have. All right. So now let's go to the next constraint. This is our next constraint. I'm going to write it here. x1 minus x2 should be equal to 350. I want to draw this line. So if I set x2 equal to 0, x1 is equal to 350. So this is, for example, here, somewhere here. This is 1 point. x1 350, x2 equal to 0. Let's find another point here. So this is a little bit tricky here. I cannot set x1 equal to 0 because x2 would be negative 350. So I'm going to do another thing. We have to find another point. For example, I set x1 equal to 700. x1 700, then x2 would be 700 minus something. It should be 350. That means x2 is equal to 350. So x2 would be 350. So another point would be x1 700 and x2 350. It would be somewhere here. Okay. So I'm going to draw the line as well here. This would be our line. So we don't care about this side, the side below the line. All right. So again, now I have to check whether the feasibility space for this constraint is on the right side or on the left side. So let's see. I'm going to give it this point again. 800 and 0. x1 is 800 and x2 is 0. x1 is 800 and x2 is 0. Less than 350. Is 800 less than 350? It's not. So this means that this area is infeasible. So the feasibility space is on the left. Okay. So the only thing that's going to happen here to our feasible space is that this area here, this yellow area, this would actually has to go away. So our feasible space would be only, I'm going to actually paint it in another color. Right, this is the green area is our feasible space. Now I'm going to show you actually a better version of this, which is not actually drawn by hand. All right, this is our well-drawn plotting of the problem. So we have our feasible space shown here on this bluish area here, this bluish area here. and the infeasible space is all in green. And you can see all the constraints are shown here. So for example, this line is x1 minus x2 less than 350. This line is 2x1 plus x2 less than 1000. And this constraint is x1 plus x2 less than 700, which was not really changing the feasible space. Okay, so one important thing about this feasible space is that any point in this feasible space, any point here in this feasible space, which there are going to be infinite number of points in this feasible space, right? So that means that you have infeasible solution in unlimited actually feasible solution here. Any point in this within this space is called interior points. Okay, interior points. So these are interior feasible solutions, which are unlimited. But if you look closer, we have some special points here. So for example, this point right here is on the intersection of two constraint lines. Also this point right here, this point right here, this point right here, this point right here. All of these points, they are called corner points. And they actually, if you look here, they make the corners of this feasible space. Okay? So these are called extreme points. And extreme points are actually very important in linear programming because there is a theorem, very helpful and important theorem, that states the optimal solution, if it exists, is actually on one of the extreme points. So this means that do not look for your best alternative within the interior points, but look for them on the extreme points. Okay, so one of these extreme points is going to be our optimal solution. So one trivial way to solve this optimization problem is to find the objective value for these points. For example, for this point, for this point, for this point, for this point, and for this point, you have x1 and x2 values. You plot it. You actually can plug it into the objective function. The objective function is 8x1 plus 5x2. So whichever of these points gives us a higher value of 8x1 plus 5x2, that's going to give us the highest profit, and that's going to be our objective or optimized solution. But there is also another way to solve this, find the optimal solution in this space, and that's actually by plotting the objective function. So the objective function is 8x1 plus 5x2. We want to maximize this. So we're going to actually plot this 8x1 plus 5x2. So give it a value, for example. 8x1, x2 equal to 500. 500 would be outside, actually. Let's give it the value that the current solution method that the manager uses, 400, or less than that, 400. Let's go with 400. So I'm going to go with 400. If I set x1 equal to 0, then x2 would be 80. So 0 and 80, somewhere here. And another point, I'm gonna set x2 equal to 0 now. If this is 0, then x1 would be 50, which would be somewhere here. So our line would be something like this. Okay. Now you can move this line to the right side or to the left side to find the optimal solution. Of course, if you move it to the left side, the last point that is going to be intersected with the feasible space would be this point right here, would be the 0 and 0. This point would be the last. If you move it on the left side, that 0 and 0 would be the last point which would touch the feasible space. So this means that we shouldn't move it to the left or down. We should move it to the right. And if you move it to the right, this point would be the last point that it would touch the feasible space before it move out. Okay, so this means this point is this extreme point is our optimal solution. Here is the last step of procedure of finding the optimal solution after you plot all the constraints. So this line that you see here, these green lines, these are the objective function for different x1 and x2. So as you see here, we have moved the objective function to the right. And this one is the last point that still touches the feasible space. And the red dot here, the red point dot here, is the actually extreme point that would be on the objective function line before it actually moves out of the feasible space. And this point is our optimal solution. So what is the optimal solution? The optimal solution for this is the maximum profit would be $4,360, which is actually $260 more than what the manager, the current production plan is making for the company. Not only that, this profit is the maximum possible profit that this company can make, given this setup problem that we have here. So based on this point, you can actually find the x1 and x2 values for this point that would render $4,360 of profit, and that would be our optimal solution, or the optimal production plan. We would say, okay, I'm gonna actually set a star here to make it x1 star and x2 star. These are going to be our optimal solution. We should advise the company, the toy manufacturing company, to produce x1 star, whatever it is. You can compute it actually based on this. I'm going to show you later. And x2 amount of the zappers. And with that production, they're going to make a profit of $4,360 in profit. Here is the summary of the optimal solution. So the optimal solution that we found, it says x1 is equal to 320. So this is x1 star, the optimal value of the optimal solution for x1, and this is x2 star, which shows they should produce 320 dozens of space rays and 360 dozens of zappers, and with that production, they're gonna make $4,360 profit. This solution utilizes all the plastic. That means that the 2,000 pounds of plastic are going to be used, and all the production hours. So for the hours of production times also have been used in this optimal solution here. So in this optimal solution, all of the plastic that they have been used, and also the production time have been used. And the total production is 680, right? If you add these up, x1 plus x2, one of the constraints was x1 plus x2 should be less than 700. So x1 and plus x2 here is 680, which is less than 700. So this constraint is feasible. Actually, all of the constraints for this solution is feasible. This is a feasible optimal solution. And a space rays production exceeds zapper production by only 40 dozens, which is less than 350, which was one of the constraints that we have. Okay, so this is our optimal solution. And we solve this problem using the graphical method.